Surface area. To find the area of a surface of some function defined on a region D, we are going to look at a small region here and see if we can approximate the surface area on that region. So as you can see here, that small region corresponds to some kind of a curved surface. And what we're going to do is use a parallelogram to approximate the area of that surface. And this parallelogram is such that the vertices of the parallelogram are above the vertices of the region that we're looking at there. So the only question is, how do we find the area of a parallelogram? Well, you might remember the area of a parallelogram formed by two vectors A and B is the magnitude of the cross product of those vectors A and B. So the only question is, how do we find the vectors A and B? Now you'll notice that A is parallel to the x-axis and B is parallel to the y-axis. And so these vectors A and B would need to depend on the partial derivatives with respect to x and with respect to y. So the question is, how much does the point change from point P here down to the end of the vector? Well, the change in x is simply going to be delta x. And there is no change in y, since y is equal to a constant value here. And then the change in z is going to be the slope of this vector here multiplied by delta x. And so the vector A can be described as the vector delta x, 0, and then fx multiplied by delta x. That's what you see right here. And then B, we can do the same thing. So for the vector B, which is parallel to the y-axis, there is no change in x. The change in y is delta y, and the change in the z value is the partial derivative of with respect to y multiplied by delta y. Now, if you take the cross product of these two vectors, you can see that we get this quantity. It's a little bit tedious, but then from there, we can take the magnitude of that vector, which is simply the square root of the squares of all of these added together. And when we're all said and done here, we actually get a pretty simple formula for surface area. To find the area of a surface above some region D, we simply need to take the integral of the square root of the sum of the squares of the partial derivatives and 1. And this is another way that we can represent that formula. So let's go ahead and do an example. In our first example, we want to find the surface area of the part of the surface of the function z equals x squared plus 2y plus 2 that lies above the triangular region T in the xy plane, and the region T is the triangle with these vertices, which you can see here. In 3 dimensions, you can see our domain down here in the xy plane, that is this here. And if you project that up onto the surface, you can see that you get this sort of triangular shape, but it's a little bit curved as well. And this is what we're trying to find the area of, this little piece right here. So to do this, first, let's just recognize that z equals x squared plus 2y plus 2 can also be written as f of xy equals x squared plus 2y plus 2. To calculate the surface area, we need the partial derivative with respect to x, which is 2x, the partial derivative with respect to y, which is 2, and we are going to take the double integral over our region D, and we have the square root of the partial derivative with respect to x squared plus the partial derivative with respect to y squared plus 1. And then this is dA. And this simplifies to the double integral of the square root of 4x squared plus 5, and then dA over our region D. Okay, so now we just need to figure out the region. So I'm going to integrate with respect to y first. And with respect to y, you can see in our domain here that y changes from 0 to x. So we'll go ahead and put that down. And of course, x is simply changing from 0 to 1. And then we have our function, square root of 4x squared plus 5, dy dx. All right, now this looks like a complicated integral, but remember, if we're integrating with respect to y, this is a constant. So this simply becomes the integral from 0 to 1 of, and now the integral with respect to y here is just going to be this thing times y. So we get the square root of 4x squared plus 5 times y. Evaluate that from y equals 0 to y equals x, and then dx. So we have the integral from 0 to 1. When we plug in x here, we just get x multiplied by that radical. And when you plug in 0 for y, you get nothing. And now we have a simple u substitution type of integral. So we can let u be equal to 4x squared plus 5. du is 8x dx. So we can put 1/8 integral. When x is 0, u is 5. When x is 1, u is 9. And we have the square root of u times du, which is 1/8 times 2/3 u to the 3/2 from 5 to 9. Doing the math here, we have 1/12 u to the 3/2, 5 to 9. And this is 1/12 times 9 to the 3/2 minus 5 to the 3/2. 9 to the 3/2 is 27, so this is 1/12 times 27 minus, and then 5 to the 3/2 is just 5 radical 5. So we can write this as 27 minus 5 radical 5 all over 12. In our second and final example here, we want to find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. So the paraboloid here, you can see in this graph, z equals 9 is a horizontal plane that intersects this graph, and the projection down onto the xy plane of that intersection is a circle of radius 3. Now the reason for that is because if z equals x squared plus y squared, the intersection where z equals 9 is simply 9 equals x squared plus y squared. And that, of course, is x squared plus y squared is equal to 3 squared, which is this circle down here, center at the origin, radius equal to 3. All right, so that is our domain, that region. And now to get the surface area, we need some partial derivatives. So we have f of xy, if you want to use that notation, is x squared plus y squared. So the partial derivative with respect to x is 2x. The partial derivative with respect to y is 2y. And our surface area will now be the double integral over our domain D of the square root of 2x quantity squared plus 2y quantity squared plus 1. And this is with respect to a, or dy dx, basically. Okay, if you multiply this out, you're going to get the double integral of the square root of 4x squared plus 4y squared plus 1 dA. But we know anytime we're integrating over a circular region, it is almost always easier to use polar coordinates. So if I bring in polar coordinates, let's just recognize that 4x squared plus 4y squared is 4 times x squared plus y squared. And we know in polar coordinates, x squared plus y squared is r squared. And so this becomes the double integral of the square root of 4 times r squared plus 1. And then dA, of course, becomes r dr d theta. And r is going to vary from 0 to 3, and theta, of course, varies from 0 to 2 pi to get the whole circle. This can now be separated into two integrals, integral from 0 to 2 pi of d theta, multiplied by the integral from 0 to 3 of the square root of 4r squared plus 1 times r times dr. This one here is very straightforward, theta from 0 to 2 pi, and then we're going to multiply that by this integral, which is a u substitution. And so we get 1/8 integral of square root of u du, and if r is 0, u is going to be 1, and if r is 3, we have 4 times 3 squared, which is 4 times 9, or 36, plus 1 is 37. Doing the math here, we have 1/8 times 2/3 u to the 3 halves, which is 1 over 12 times u to the 3 halves from 1 to 37, which is equal to 1/12 times 37 to the 3 halves minus 1 to the 3 halves, or 1/12 37 radical 37 minus 1. And that's that one. So if I bring that over here, now I just need to multiply that by this integral, but this is simply 2 pi minus 0, which is 2 pi. So if I multiply these together, we're going to end up with pi over 6 times 37, radical 37 minus 1. And that is the surface area of this. So that is the area of all this surface that you see here. Okay, because that is the surface of the function that is above this disk in the xy plane. And that concludes this video lesson.